What does quantum mechanics reveal about the hydrogen atom? That's a question that Atkins poses in his book. That's the book that I use in my honors general chemistry course. That series of slides that I'm going to go through within this discussion, this is what I share with that particular class. Um, and here's sort of an outline of what we'll step through. We're going to be looking at those first features leading to the idea of quantum numbers and what they're describing. And then in a subsequent video, look more closely at describing the shapes of the orbitals. So the storyline thus far is we've explored the Schrodinger equation and have a sense of operators, wave functions, and the how it returns the corresponding eigenvalues. When looking at that for different systems, we would have a description for the kinetic energy and the potential energy. If we're looking at the particle in a box model, the potential energy is 0, so we're only interested in the operator corresponding to the kinetic energy. Here's the solution, the resulting wave functions for the particle in the box and their energy values. A visual depiction for the different ones as the quantum number increases, we see a change in the wave function. And then linking the wave function to the probability density. The square of the wave function was giving us insight for where the particle was found in the box. Extending that to a three-dimensional box, instead of just having along, let's say, the x, we would have values along the x, y, and z. We can separate it into the component parts. We know the answer for the one-dimensional, and we see the answer repeated again for the x, y, and z. We could express the entire thing in terms of combining those, let's say, in terms of the volume. And the energy looks very similar to what we saw for the one-dimensional box, but we would have now quantum numbers and lengths describing each of the dimensions in the box. These would then be some depictions for what the wave function would look like depending on the quantum numbers. I'm bringing this all up to point out, well, is this what the atom looks like when we think about where the electron is found? Does it have shapes like this or something else? In this analysis for the box, we extended it to 3 dimensions, but it still had 0 potential energy. Key thing when we extend it to the hydrogen atom is we need to account for a potential energy term. We're again going to be looking at wave functions. They'll be in 3 dimensions. We can have a Hamiltonian describing that, but notice our Hamiltonian, we cannot say the potential energy is 0. The description for the potential energy depends on the attraction between the electron and the proton. So we have a charge describing charge of the electron, charge of the proton. And this potential energy term, this is what is being added in now when we're seeking a solution for the hydrogen atom. Looking within the Atkins text, points out that this is what the Schrodinger is seeking to find a solution for the hydrogen atom. And it's not a simple task. Along the way, within his analysis, we find that there's this grouping of fundamental constants that matches up with the Rydberg constant, pointing out that this is one of the triumphs of his analysis, the agreement between these fundamental constants within his derivation and this experimental quantity. There's the description for what we would call hydrogen-like atoms then. So these would be ones where we can vary the number of protons, but so that's what the Z term is. We can vary the number of protons within that, but we only have one electron. That's what the description hydrogen-like means. There's a linking then with the energy levels and then the permitted values for the hydrogen atom, connecting it to the different spectral lines. And reiterating once again that the Z value is the nuclear charge. That's going to be very important as soon as we move beyond having a single proton. So within our analysis, yes, we're doing it for the hydrogen atom, but we're going to then extend it to all the other wonderful elements that we find on the periodic table. So the solutions to the Schrodinger equation are the atomic orbitals. We're interested then for spatially around the nucleus, what is the value for the wave function when we are looking at then the solution to the Schrodinger equation. As Atkins points out, it's going to be convenient to describe these in spherical polar coordinates. So there's a little bit of text there and then an image showing what we're going to need to have. We're going to say that the nucleus is in the center. There's a distance that will travel out r. And then with two angles, we can then describe any other feature spatially. So we won't necessarily be doing the math on this, but we want to note that there are two different features. When we look at our wave function, it's going to have a radial component that describes moving from the center outward, and then an angular component that depends on two different angles. These are the three-dimensional standing waves that we'll be looking at for our atomic orbitals. Here's the overall generalized equation. The quantum numbers that we're familiar with, n, l, m sub l, those are found within this generalizable equation. So when we say, well, what is the solution? This is our solution, and then we're picking different n, l, and m sub l values and putting them into this overall expression. That gives us our wave function that has a radial component and an angular component. These are then solutions for our hydrogen-like wave functions. First of all, looking at the radial component. So the radial component is described using the values n and l. And then taking the values and calculating it, this would be the corresponding radial wave function. So we know that n begins at 1 and increases from there, 1, 2, 3. We are also having the radial wave function described by a L value, which describes the shape for the angular momentum. Those are the values then that correspond to what we know as S, P, D, or F orbitals. So we have a 1s, a 2s, a 2p, a 3s, etc. Paired with those then is an angular wave function. So depending on the L and M sub L value, we have a corresponding angular wave function that goes with it, and we have allowed values for those. So this would be an example for a 2px orbital. We have two different features. Well, we have n, l, and m sub l values. We have a radial component that went with the 2p, and then the corresponding angular component. So that big equation, this is showing how it fits together for the different parts. So if you had a 1s, you'd be combining this radial component with this angular component. A few general observations. So even though we have perhaps some very complex mathematics being shown here, let's connect it with what we know when we have our simple rules describing the quantum numbers. The radial component depends on the n and the l value. The angular component depends on an l and an m sub l value. We have different what are called radial nodes. If we look at the radial component, if we start from the center and move out there, the sign of that can depend on the distance. This leads to radial nodes. So just like within our particle in a box for a one-dimensional one, we would have, for example, if we fit one whole wavelength in that, we would have a radial node or a node halfway in between where the wave function crossed the zero value, and it would have both a positive and a negative region. Same thing that we're thinking about here when we're looking at these radial wave functions. If we look within the sign for these, we see there's examples where, depending on the value for r, it could have both a positive and a negative value. It could, a negative region. It could change its quantity. So in these particular examples, if we're having a general description for a radial node, at the bottom there I show how we can combine the quantum numbers to get it. The n value minus the l value minus 1 tells us the number of radial nodes. So if we do that math, take a second and do it for each of the ones in the boxes. N equals 1, l equals 0, n equals 2, l equals 1, n equals 3, L equals 2. In each case, if you did n minus L minus 1, you'd find that you end up with a value of 0. We're not seeing a change of sign depending on the distance r. If you do the math within these, you'll find that it does change. So within these examples, depending on the value of r, you're introducing radial nodes. So the first time that you have a particular L value, a particular type of orbital introduced, you do not have any radial nodes. So for a 1s, a 2p, a 3d, those are all examples where you do not have radial nodes. After that, it goes up incrementally from there. You can also have spots where your wave function crosses 0 depending on angular ones. So if you notice there for the angular wave function for L equals 0 for an s orbital, there's no angle that you can pick in which it's going to equal 0. The angular wave function will never equal 0. If you look for a p function, a p orbital, you could pick an angle in which it will cross 0. So a p orbital has an angular node, whereas an s one does not. So within here we have then, we're connecting the different quantum numbers to the our typical energy diagram, where we have our principal quantum number n equals 1, 2, 3, the L sub 0 value corresponding to, if we're looking at S, L equals 1, RRP, L equals 2, RRD, and then our allowed quantum numbers, where we break it out from negative L to positive L for the M sub L values. And then in the hydrogen atom, we're lining these up based on the principal quantum number. So the 2s and the 2p would be degenerate, have the same energy values. Here's then activity that the students would work through, where we're comparing in the hydrogen atom what happens if the electron goes from a 1s to a 2p orbital, or from a 2s to a 2p orbital. I'm bringing this up because a lot of times the students would say, well, a hydrogen atom, there is no 2p orbital. It's only a 1s. They're saying that they know what the ground state electron configuration is, but just like within our simple Bohr model, we saw that there were excited states where the electron can move to. That's what's showing up here. A hydrogen atom can be in a 1s and move to an excited 2p. It could be in a 2s and move to a 2p. Important thing when answering these is we're looking at a hydrogen atom. So for the values, if we're looking at the 2s and the 2p, for the hydrogen atom, they're degenerate. So if I move from a 2s to a 2p, the energy is not changing because the n value is not changing. We also spent a little time talking about allowed and not allowed quantum numbers, and also the corresponding orbitals that go with those. One more idea within here is a phenomenon called the Zeeman effect. What happens here is that if you apply an external magnetic field, our different spectral lines split into additional multiple closely spaced lines. So what I'm saying within that is that you can have a single transition that now appears to be split out in that symmetric manner. This is what's called the Zeeman effect. And that's why we have M sub L be a magnetic spin quantum number. It corresponds to the change in the spectra when we're doing the experiment now in an applied magnetic field. And at the bottom here, this is from the Hyperphysics website, we see what's going on. So instead of having them be degenerate based on simply their L value, with the M sub L value when it's placed in a magnetic field, splits them out, separates them out, and now we have additional transitions possible. So within this video, we quickly reviewed a few findings from our particle in a box and saw how the Hamiltonian led to particular solutions. We're doing the same thing now when we're thinking about atomic orbitals, and seeing that to describe them with quantum numbers, we have both a radial and an angular component. And those are what the quantum numbers then match up with. We saw some quantum numbers that were describing the radial component. Others were describing the angular component. And thus far, the ones that we would be considering would be N, L, and M sub L. In a subsequent video, we continue on and see what does this now mean spatially and what the radial function is really telling us.